Hi, welcome to Dissolve Chemistry. In the previous video of thermodynamics, we discussed regarding thermochemistry, and lastly we concluded with defining thermochemical equation. So let us begin our discussion by revising what do you mean by this thermochemical equation. So thermochemical equation is a balanced chemical equation where the physical states of the reactants and products are mentioned along with enthalpy of reaction. So the change in energy of the reaction is also being mentioned along with the balanced chemical equation. If we do that, so then it is called as thermochemical equation. Now there are many conventions. Okay, those conventions we will see after defining enthalpy of formation. So prior to that, so let us begin our discussion with enthalpy of phase transition. So what do you mean by this phase transition? Suppose any substance, if it is in the solid form, now if you convert this into liquid form or liquid state, okay, and into gaseous state, or directly from solid to gaseous state, okay, and in the reverse order, gas to liquid, liquid to solid. So like that, the interconversion from one physical state to the next another physical state, so we call it as what? Phase transition we call. And always remember, these phase transitions are accompanied with a amount of energy change during that process. Particularly, we will see one by one in that. Suppose we are converting from solid to liquid, okay, and this conversion of solid to liquid will happen at a particular temperature and at constant temperature and constant pressure, okay. Whatever the amount of heat is absorbed or evolved, so that we call it as what? Enthalpy of a phase transition. So in that, so again we categorize them into what type of phase transition we are bringing into different categories, that is enthalpy of fusion we call. Okay, so enthalpy of fusion. So what this enthalpy of fusion involves, so we write like this. Okay, we are going to mention like this, fusion H. Okay, standard enthalpy, if we are maintaining the condition standard, we can make it as, or standard enthalpy of fusion means fusion, already we have said, conversion of solid form to the liquid form. So always it is what it involves. Conversion of solid to liquid of any substance is endothermic process, means heat is absorbed. Therefore, enthalpy of fusion for any substance will be always positive. So for example, let us consider, okay, to understand the definition of this enthalpy of fusion. Say for example, I will write H2O liquid. Okay, we will write like this. So to convert this, so at this temperature, constant temperature, that is 273 Kelvin or 0 degree Celsius and 1 bar pressure, if we want to convert solid water into liquid water, that is ice to water, so then the amount of heat energy absorbed at this temperature is called enthalpy of fusion of ice we call, and it is around flux 6.0 kilojoule per mole. Now suppose if you want to convert same liquid water into ice, okay, at the same temperature and pressure, then your enthalpy of fusion will turn back into what we call it as enthalpy of condensation we call. Okay, so therefore, so what happens? Its sign will change, means the same amount of the heat what is being absorbed to convert solid to liquid, the same amount of the energy is given out when we convert liquid into solid at the same temperature and pressure. Okay, so then next type of enthalpy, that is enthalpy of vaporization. What do you mean by vaporization? Conversion of liquid form to vapor form or gaseous state. Gaseous state. So now liquid formed to vapor or gaseous state. So whatever the amount of energy absorbed, already it is also an endothermic process. At a constant temperature, that temperature should be its boiling point or boiling temperature, and at atmospheric pressure, whatever the heat is absorbed to convert this liquid into vapor form, that we call it as what? Enthalpy of vaporization. Let us consider an example. So that liquid water, at a constant temperature, that is its boiling temperature, that is 373 Kelvin, and 1 atmosphere or 1 bar pressure. So whatever the amount of heat is absorbed, so to convert this liquid into vapor form, so we call it as gaseous state. So that enthalpy, we call it as what? Enthalpy of vaporization, right? If it is 1 mole, so then, and standard conditions, that is 373 Kelvin, that is its boiling temperature, constant, and 1 atmosphere, which is also constant. So therefore your standard enthalpy of vapor, it is equals to plus 40.76 kilojoules per mole. So now this is what we call it as enthalpy of vaporization. And third important, again you can ask the question that if you want to condense the same gaseous phase into liquid phase, so gaseous to liquid phase at the same temperature and same pressure, the enthalpy change will be there, no? Its sign is going to change, that is plus will convert into minus, because that much amount of the heat is given out when you condense the 1 mole of water to liquid water, gaseous water to liquid water. Then next we will talk about enthalpy of sublimation. What it involves? It involves enthalpy of sublimation. So that same example we will continue with. So now suppose if you want to convert this ice directly into its vapor form. So whatever the enthalpy change is there, so that enthalpy change we call it as what? Enthalpy of sublimation equals to enthalpy of sublimation is equal to plus 46.76 kilojoules per mole. Now you might be wondering that how we get this 46.76. Now you are converting solid to liquid and liquid to vapor. Solid to liquid, 6 kilojoules per mole energy we are getting, means so ice to water, liquid water, 6 kilojoules per mole amount of energy is being utilized, or it is being absorbed at its what temperature? So at 0 degrees Celsius. Similarly, liquid to what we are converting? Vapor. So their amount of energy absorbed is 40.76 kilojoules. So therefore, now if I convert solid to vapor directly, so then it will be what? Sum of these two energies if we supply. So then what happens? We will be getting total enthalpy of sublimation. There are many subliming solids are there, like naphthalene you can take, naphthalene sublimes to give, this is solid, to give naphthalene vapors, delta H of sublimation equal to 73 kilojoules per mole. Okay, so this is how we are going to define different enthalpies of phase transitions. Okay, now let us move on to the next very important enthalpy, that is enthalpy of formation. Standard enthalpy of formation. So now what is the standard enthalpy of formation? Now we will be having different compounds are there, and these compounds are formed by what? By the combination of the elements. So now when the combination of the elements, okay, leads to the formation of the compound, during which whatever the enthalpy change is there under standard conditions, that we call it as what? Standard enthalpy of formation. So the standard enthalpy, so when 1 mole of the compound is formed under standard conditions and constituent elements are also in their standard state, or we call it as what? Reference state. What do you mean by this reference state? The most stable state of that particular element under a given conditions of temperature and pressure, we call it as what? A reference state. And that combination of the two different elements to form a compound is called as enthalpy of formation. If you are maintaining the standard conditions, then we mention it as a standard enthalpy of formation. For example, so let us take formation of 1 mole of water. For that what we need? H2 gas plus half O2 gas. Then it will give 1 mole of H2O liquid in the standard state. Okay, liquid is the standard state, that we minus 288.8 kilojoules per mole. What does it means? When 1 mole of liquid water is formed by the combination of its constituent elements, that is hydrogen and oxygen, in 1:2 ratio, then the amount of energy released will be 288.8 kilojoules per mole. So that is enthalpy of formation of water, we call. Similarly, you can take enthalpy of formation of, okay, so carbon, graphite, methane we will take, that is graphite solid, which is the standard state of the carbon. Now it is combining with 2 moles of hydrogen gas, both are in standard state. So now when they combine to form CH4 gas, okay, so delta H minus 74.81 kilojoules per mole. Okay, so that is what we call it as formation of methane. Similarly, if you want to form ethanol, what you have to take? Say for example, carbon graphite in standard state. Okay, this is also in standard state. Graphite, right, 2 moles I have to take, plus here how many hydrogens we need? 6 hydrogen atoms will be there in ethanol molecule. So therefore 2 moles of hydrogen gas plus half mole of O2 gas we have to take. So then it will give C2H5OH liquid. So then enthalpy of formation of ethanol minus 277.7 kilojoules per mole. Okay, so this is how we can define enthalpy of formation of different compounds from their elements. Means it is purely combination of elements to give the compound, we call it as what? Enthalpy of formation. Now the question may arise. Let us take one example and then illustrate what it exactly means. Suppose you take a calcium oxide solid plus CO2 gas in its standard state of the gas, and it will give calcium carbonate. Now So is this reaction is a enthalpy of formation minus 178.3 kilojoules per mole. Okay. So now look into this. So when we look into this equation, what we see is that it is not a combination of elements, instead of it is a combination of two different compounds to give another compound. So here whatever the enthalpy is there, no, this enthalpy we won't call it as what? Enthalpy of formation. What is the reason for that? So enthalpy of formation we only apply for those reactions where the combination of elements in their standard state leads to the formation of the compound. But here what it involves? It involves the combination of the two different compounds to give another third compound. Okay, so therefore it is not an enthalpy of formation, we can call it as what? Just enthalpy of a reaction. And please refer in the books the various standard enthalpies of formation of simple compounds are being given in many books, so please refer that one. Well, I am interested to know about the enthalpy of this reaction. Then how to know this one? Calcium carbonate, okay, solid, okay, it will decompose to give calcium oxide, that is lime, solid plus CO2 gas. And I want to know about the change in enthalpy of this reaction. So to know that one, how we can do that one? So we know that delta H of this reaction, okay, delta R of this reaction will be equals to what we can say for standard, we will take standard enthalpy of this reaction is equal to summation of enthalpies of the product minus summation of enthalpies of the reactants. Okay, so enthalpies of the products are what? So therefore that is enthalpy of formation of calcium oxide plus enthalpy of formation of carbon dioxide, okay, minus enthalpy of what? Enthalpy of formation of calcium carbonate. So from this we can calculate the enthalpy of reaction. Okay, so you substitute the value of enthalpy of formation of calcium oxide. This we can form by combination of calcium element and oxygen element. Similarly, we can calculate this by carbon dioxide, enthalpy of formation of the carbon dioxide. And finally, enthalpy of formation of calcium oxide is 635.1 kilojoules per mole. Similarly, enthalpy of formation of carbon dioxide in the standard state will be 393.5 kilojoules per mole, and whereas of calcium carbonate is 1206.9 kilojoules per mole. So overall, when we calculate, then the enthalpy of this reaction, above reaction, we will get, okay, standard enthalpy of this reaction we can calculate like this. Means if we know the enthalpy of formation of different compounds, so from the thermochemical data of that we can calculate enthalpies of reactions of very different types of reactions we can calculate theoretically. Okay, so wherever it is not possible to find it directly. Okay, so now we will discuss regarding conventions used in expressing the thermochemical equations. See here we will write one thermochemical equation. Example as combustion of ethanol molecule we will take. Okay, liquid plus O2 gas, 3 moles you have to take. So upon complete combustion it will give 2 moles of CO2 gas plus 3 moles of water it is going to form. Okay, liquid state, and this is gaseous gas. Okay, and enthalpy of reaction, okay, right, enthalpy of reaction, okay, that is equal to minus 1367 kilojoules per mole. Now when we look into this equation, okay, so right, the stoichiometric coefficient in the thermochemical equation always represent number of moles but not molecules. And the enthalpy change what we have mentioned here, it will be always corresponding to the stoichiometric coefficient what we have mentioned here, but not it corresponds to per mole. Okay, so therefore, so whatever the enthalpy change for a reaction is mentioned in the thermochemical equation, it is always corresponds to the whatever the stoichiometric coefficient we have taken in the reaction. Enthalpy change value always corresponds to the stoichiometric coefficients mentioned in the reaction, mentioned in the thermochemical equation. Okay, so this let us illustrate. Say for example, suppose I am doing reduction of iron oxide. So it undergoes reduction in presence of 3 moles of hydrogen, okay, to give 2 moles of iron solid, okay, plus 3 moles of water it is going to form, and overall enthalpy change for this reaction will be, okay, so it is minus 33.6 kilojoules per mole. Okay, now what I am doing, instead of 1 mole, if I take half mole, say for example, okay, Fe2O3 plus 3/2 H2O to give Fe solid plus 3/2 moles of water, then your enthalpy of reaction what we have mentioned here, it will also be hauled into 2, okay, delta H of reaction by 2. So therefore minus 33.6 by 2, so which is equals to what? Minus 16.6, okay, 16.8 kilojoules per mole. So what does it means? Means if you are mentioning the enthalpy change for a reaction, now suppose if you divide that equation, or stoichiometric coefficients are divided either by 2 or 3, whatever may be the coefficient, so then what happens, your enthalpy value has to be divided. Okay, if you are multiplying this, if you are increasing the stoichiometric coefficient, in the meantime enthalpy of reaction also to be multiplied with that particular factor. Okay, so that is what is the meaning of this second point. And the third important point, now say for example you consider N2 plus 3H2 gas combined reversibly with to give 2 moles of ammonia gas. Okay, so now the enthalpy change for this is minus 96.6 kilojoules per mole. Okay, now suppose I am carrying out this reaction in reverse direction, means I am taking ammonia and I am decomposing to give N2 plus 3H2 gas. Okay, so now what happens to your enthalpy of the reaction? Just the sign of this enthalpy of reaction is going to be changed to minus sign into plus sign. Okay, so that is how we do that one. Means if you reverse the reaction, then the sign of the enthalpy of reaction is going to change. Okay, so these 3 important factors we have to remember, and apart from this, these thermochemical equations we can add, we can subtract. Okay, and whenever you do the reverse of that reaction, if you reverse it, then the sign of the enthalpy change should be reversed, means plus to minus, minus to plus. I hope you have understood the concept. So in this video we have discussed regarding enthalpy of phase transition, enthalpy of formation, and then important aspect that regarding thermochemical equation, what we have to keep in mind when we are going to alter it. Okay, thank you for watching, and please subscribe our channel to view more videos of the subject. Thank you.